Hello and welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video I will tell you about neural networks in a nutshell. In the end, you should know the basic computational unit of a neural network. You should know the basic architecture of the neural network and understand the basic concept of how learning works in a neural network. The very basic computational unit of a neural network is called perceptron. Here is a visualization of this perceptron. As input, we have a feature vector, as usually also for other learners. So we have features x1, x2, x3, and so on until xp. What we first compute is a linear combination of these features. Linear combination means basically x1 times theta 1 plus x2 times theta 2 plus, and so on. So the same thing which you already know from a linear model. And then we add something which is in the neural network community called a bias, which perhaps a statistician we would call intercept. Okay, so basically it's just a theta 0. So let's perhaps connect these two things because they belong together. So that's just a usual intercept. So what happens until here is really just what always we do in a linear regression, linear model, just linear combination of the features. Then a second step, we can have an activation function. This may be the identity, so nothing happens at all, then we still have a usual linear model. That's the first option. The second option is that this activation function is a logistic function. So this sigma of x, which is exp of x divided by 1 plus exp of x, okay, which you know from logistic regression. And basically, if we use this logistic activation function, then this perceptron is the exact same thing as a logistic regression. It's not just somehow similar or related, no, it's really mathematically exact the same thing. Okay, that's very important. It's just all this neural network thing and connections, activation is just, let's say, a visualization and intuition on this, but it's mathematically exact the same thing as a logistic regression. Of course, we can have other activation functions, and it's not anymore logistic regression, but up until here, it's really what you already know beforehand. Now we can take these perceptrons and stack them together. So we can have several units which are connected to the inputs, and the set of these units is then called one hidden layer, and we can have several of these hidden layers. So the number is, well, up to you. You can do whatever you want. The architecture is your choice. It's perhaps a hyperparameter of the model, but in each hidden layer there can be several units, and the number of units doesn't have to be the same in all the layers. And then you have one output layer. And basically this output layer is again just perceptron, because if you think of these nodes here in the last hidden layer just as somehow transformed features, then it's just really again just one perceptron. So we can also say that everything that happens here is just a very fancy feature extraction or feature transformation pipeline. In the end, we just have one perceptron. And depending on the activation functions, can be regression or classification. What we can do, if we want, is that we do the following, that we add perhaps a second and a third output node, which is also connected to everything. This would then be the case if we have, for example, a multi-class classification. Okay, then this would be the output for class 1, class 2, and class 3, and then we would get scores for all the 3 classes, and then we would have to make some choice how we aggregate these perhaps just take the class which has the maximum score as final prediction. But it's very simple to extend this to the multi-class case. So, to wrap up, the hidden layers are ordered such that the output of hidden units serves as input for units in the next layer. So we have a direction of these feed-forward networks. It's also called, there are others, which we do not treat for now. And one caution, if you have too many hidden layers or too many units per layer, this can lead to overfitting. So neural networks are known for its overfitting behavior. So we need some tricks later on to counteract this overfitting, of course. Then, regarding the output layer, the number of output units depend on the task, and different activation functions for output layer and hidden layers are possible. So you can, for example, have some sigmoid activation here, but for example, some ReLU activation in between. ReLU is the rectified linear unit. You will hear more about this later. Okay, how does learning work in a neural network? We decided to give you an example of image classification, which is perhaps slightly more complicated, but basically the idea is the same. So then at least you have seen this already. So this is an iterative approach. First we have a forward pass, then we have something called backpropagation, and this goes in a circle on and on and on and on until we are finished. So how does this work exactly? Here is another neural network architecture which is used for image classification. Let me first very briefly explain you how image classification works in a neural network, or in this convolutional neural network, CNN, because we have these convolutional layers here. Okay. Input are labeled data, images. So how are images represented in a computer? Well, you have those red, green and blue values for each pixel, or perhaps just a gray scale for each pixel. So let's say this is one image, just 9 pixels, a 3 by 3 image, gray scale, so we just have 9 numbers here. And then, well, we have several images in the data set, and for each image we have the true label, which we need for training, of course. What convolution does now is that we move a sliding window of a small filter, which has to be smaller than the input image, let's say 2 by 2. We move this over the image and compute a convolution of the filter and the part of the image that we can see with the filter, and store, well, the result of that convolution here. So basically, if we have a 2 by 2 filter and a 3 by 3 image, then we have 4 possible convolutions, which is why we have 4 values here. Just a very quick introduction to this. Then we pool this somehow. For example, we just take the maximum value of this, and then we can have more convolution and pooling layers, convolutional layer, pooling layer, and finally, and we have one or more fully connected layers, which are these usual perceptrons, which you have seen before. So if you did not really follow here, that's not that bad, because we will speak about this more in detail later. The important thing is that, as before, we can just say, okay, in the very end, we have just a perceptron. Okay, we can say everything which happens before is just a fancy way of feature extraction. Okay, we can just say, okay, that's x1, x2, x3, and so on. Okay, so we have a perceptron in the end, which means that we get for each image a probability that it belongs to class 1, in this case dog, with the true label and predicted probability we can compute a loss. Okay, and now the training is based on this loss, because we can now, for example, do gradient descent and move backwards in this architecture, and so in that direction, and say, okay, we know the loss, we take the derivative of the loss, and we look, or we ask ourselves, in which direction do we have to change the weights or update the weights such that the loss gets smaller. So we go all the way backwards from the very beginning, from the very end of the neural network to the very beginning, and change all the weights a little bit by updating them. And then we do a forward pass, compute the new loss, because perhaps we have a new prediction. We take it in the derivative, go back, update the weights a little bit, go forth, update the loss, go back, update the weights, so on and so on, until we, well, have to stop somewhere. So there will be some criterion which tells us when to stop. We'll see more about this later. But at the very end, we have estimated or computed a lot of weights in this neural network. So, for example, the values in these filters here, which we have more than just one of them. Also, the weights in these fully connected layers, and then it's finished. And if we have a new prediction, a new observation where we try to find a predicted value, then we just do one forward pass, just once, get the probability and threshold this and get one final prediction. One last word on the effect of hidden layers. So what happens here is that these layers learn more and more abstract representations when we go deeper into the neural network. So in the very first iteration, very easy things are learned, like colors or shades of colors. And then if we go further, we have slightly more complex things like lines and boundaries from white to black and from black to white and so on. And the deeper we go into the network, the more complex and complicated are the things that we learn here, so that the network at the very end is able to learn or to have a representation of quite complex things of the world. We could also say that each layer adds some degree of nonlinearity, and in the end, these neural networks are really well performing for a lot of different tasks. And of course, there are a lot of different architectures, so not just the fully connected layers or just those convolutional layers, which I showed you right now. There are very different types of architectures, also architectures where we do not only have a feed forward, a forward pass, a prediction, and so on. But we will see more of this later. That's it for now, for the nutshell, or for neural networks in a nutshell.